In the previous section, we assumed that when a wave encounters a boundary, it's transmitted through the boundary. So actually what happens when a wave reaches a boundary or an obstacle in a medium is that part of the wave will be reflected and part of the wave will be transmitted. For now, let's consider what happens to that reflected portion of the wave. There are generally two cases. The first one we'll look at is fixed end reflection. A fixed end can occur when a wave encounters an obstacle like a wall, or when it reaches any kind of medium that's more dense than the first medium. So this is why I've drawn two examples here, one where it looks like a wall or a fixed support, and then in the second case where it's moving to a more dense string. So again, we're considering waves in a string for this section. When that wave reaches a fixed end, what happens is the part of the wave that is reflected is inverted. Why this happens is because of Newton's third law. The wave will exert a force on the boundary and it exerts an equal and opposite force back on the wave. So it causes that portion to be reflected. I've drawn here in the string the part that's transmitted as well. That transmitted portion would still remain upright. Okay, let's look at the other case. Okay, the second case is free end reflection. So in free end reflection, the end of the string is free to move. So in the first case, we can imagine that it's just free to move. It's kind of hard to picture how this would work horizontally, but you could picture a string that's hanging vertically and then the end is free to move. What happens when the wave reaches the end of the string is the part that is reflected is reflected, but it remains upright. This is basically because there is no reaction force to invert the wave. This is similar to when we have a wave in a string traveling from a more dense string to a less dense string. That behaves as a free end. So if it's moving from more dense to less dense, the reflected portion remains upright. Now, in both of these cases, as a wave travels from one medium to another, part of the wave is reflected and the end part is transmitted. The part that is transmitted will always have reduced amplitude. Actually, both parts will have reduced amplitude compared to the original wave, since the energy of the wave is split across the boundary. So the part that is transmitted, it will have the same frequency as the original wave. That frequency is set by the wave source, so it's constant as the wave travels, no matter if it moves from one medium to another or not. The wave speed, however, is set by the properties of the medium. So if it's a string, we can calculate it as we did in the last section, v equals root ft over mu. If it was another medium, it would still depend on the properties of that medium. So the speed will change, and then the wavelength will change as well. Because if the frequency is constant, the wavelength must depend on the properties of the medium as well. So it's important to remember that the frequency is constant there. Let's again consider a wave on a string. If the wave source is continuous, what will happen is that waves hit the end of the string and are reflected back, and they collide in a sense with waves that are still being produced from the source. This gives rise to interference. Interference is what happens when more than one wave occurs at the same place and the same time. And interference is governed by this principle of superposition. The principle of superposition says that when two or more waves pass through the same point, the resulting wave function is the algebraic sum of the individual waves. So our new wave function y at x and t would be the sum of y1 at x and t plus y2 at x and t. And there are two types of interference. Okay, the two types of interference are constructive and destructive interference. Constructive interference occurs when two waves meet and the resulting waveform has a greater amplitude than both of the two individual waves. I've drawn a case here of maximum constructive interference where we have two identical waves that meet and then they produce a wave with twice of the amplitude of one of the individual waves. Destructive interference occurs when two waves meet and the resulting wave amplitude has an amplitude that's less than at least one of the individual waves. So I've drawn here maximum destructive interference, which occurs when we have one wave of positive amplitude meeting with a wave of negative amplitude at that specific point, and those waves will cancel completely so that the resulting wave amplitude is zero. There can be destructive interference that's less than this as long as the wave amplitude decreases. So after this point, the waves would continue on unchanged. The interference only happens when they're meeting at that specific point in time. There's some examples of this. You've probably heard this before with sound speakers when they interfere. This is the same interference since sound is a wave. Also, if you were to shine two flashlights and they would interfere to produce a brighter light, that would be interference too. Interference also happens with sinusoidal waves, and we'll look further into that case in the next section.